Welcome to the lecture of October 6. I emphasize the date because October 6, 2020 is also the date where the Physics Nobel Prize has been announced. And you may have already learned that the prize in this year went at least to one half to a theoretician, Roger Penrose, and to the other half to experimental physicists. And because at least the theory part is certainly very much related to what you are actually going to cover in this course, I wanted to spend some minutes first to tell you a bit about what this prize or what the content of the discovery is that led Penrose to receive this prize. So it's of course a nice coincidence that during the time you take this lecture, we also have this, let's say, popular thing happening that a very important discovery gets a Nobel Prize. It would have been even better if the Nobel Prize was given maybe a month later, because then I could have explained to you on a slightly more technical level what that all means. But we will certainly get to that, and I will come back in a month or whenever we have the tools necessary to this discovery by Penrose and others. Nevertheless, it also very fits very nicely into the motivation of what we are going to do today. And so maybe you remember that we have often drawn diagrams, and I always had on the left-hand side of my slides or of my whiteboard presentation a manifold. And now instead I just put the picture that was relatively recently taken of a black hole. So you should really imagine always when I have on the left-hand side this abstract drawing of a manifold, that's the real thing that is out there. And of course that picture, by the way, of course, is essentially the picture of light we see that is around the black hole. So we don't really see the black hole, and what you are interested in to understand is the matter that is there, but also the geometry of space-time. And what we did usually when we had this manifold on the left-hand side, then I said, because it's a manifold, there are chart maps. So maybe you remember we had these arrows and chart maps that I called X and Y and so on. And then we had representations of the manifold. Of course, the manifold is this real space-time manifold is a four-dimensional manifold. And so the diagrams or the representations are also four-dimensional. Nevertheless, obviously, for obvious reasons, I have to draw them two-dimensionally, and one usually restricts to certain coordinates that are particularly interesting. And you see that real black holes, they are not spherically symmetric. Nevertheless, they have still a good spherical symmetry in the same way as Earth is spherically symmetric. Of course, not perfectly, but it makes sense to, for example, talk about radial coordinates. So I could talk about a radial coordinate, but a whole right-hand side. So everything going to the right here or the horizontal direction would be a space direction. Whereas towards or in the vertical direction, we have something like time. And so the question is, of course, how do we choose these coordinates? What are good coordinates? And a very natural choice of coordinates would be to say that we are far away, and we have, of course, a time direction. We also have a space direction. And so we just associate the coordinates that are natural to us as remote observers. However, then we enter into a problem, because what you will see is that at some point as you get, let's suppose, these are radial coordinates around the center of the black hole. So radius 0 here would mean you're really in the middle of the black hole, if you would imagine this to be some traditional object that has an actual center. Of course, that's already something that may not be there in reality. However, what you will find when you do these coordinates and extrapolate them towards the black hole, that there is a certain radius, and this radius is explicitly 2gm, where g is the gravitational constant and m is the mass. And if you set the speed of light to 1, then this is actually a length scale. So 2 times g times m, where m is the total mass of the black hole, gives you a length. And when you are exactly at this distance, all these coordinates that are reasonable from far away start to diverge. So you will see that lengths that in the diagram look very short, like if I look at 2 points and measure how much proper time do I have between those, or what's the length between those, then in the real thing, if I go back with this chart map, it would correspond to a very long length or a very long time, and actually divergent time or length. So in other words, what I'm saying here is that the coordinates get worse and worse as I approach this red line. And indeed, one can even then, I mean, we have already learned about curves on the manifold, and I could now draw the world line of someone who approaches the black hole and tries to enter the black hole. So the world line may look like something like this, but as it approaches this red line, this radius, it will asymptotically get closer and closer, but never pass it. So in these coordinates, it looks as if nothing can actually enter the black hole. And in these coordinates, you cannot describe anything entering the region that is closer than 2gm from the center of the black hole. And what I've drawn here, so this region, I mean, this region here is of course actually a sphere, because I dropped essentially the angular coordinates. So that's a sphere at radius 2gm around the black hole. This is what is now called the event horizon nowadays. But the question, of course, is what does this event horizon mean? Is this a region we cannot even cross as suggested by these coordinates? Now it turns out, and I mentioned that already, that no, the answer is not. We can cross this event horizon very easily even. And the only reason why it looks as if it couldn't be crossed and why these lengths and so on diverge was that the choice of this chart map X is a very bad choice if I'm interested in the region close to this horizon. And there are much better coordinates. And in better coordinates, I still can draw something like this. There is something like space. It's no longer R, but I'll just indicate there's some space type coordinate, and there is a time type coordinate. And in this diagram, this red line that I have on the left may look just as something like a diagonal, but the important thing is I see a much larger region. So I see somehow something that looks like this. Maybe I'll just explain in a minute what that means when I say I see that. So this is called the singularity. This is called the singularity. So again, this is just somehow a chart that represents a part of the black hole, but the point is this is a much larger part of what is physically there. So this diagram, these are coordinates that are much better to actually explain what's going on here. And you see, what if you think of chart maps, as we did last time, you could imagine that if I go backwards with the x, so I take the x minus 1, or I look what is actually the chart domain, then the chart domain of this map, let's make it green, may be something that is essentially at the outside of the black hole. Maybe it's this region. Of course, it would be actually spherically symmetric, so that would be a bad diagram, but it's essentially the region outside of the event horizon, where this is good. Actually, the event horizon is probably here, and what this diagram represents is the part outside. Whereas the diagram that I drew below, that one, may cover actually the full thing, including the middle that is not covered by the other chart. And it even covers more. It even covers stuff that you don't see on this picture, and this corresponds to this part and maybe this part. These are extensions that we are not even sure they physically exist, but they're mathematically valid extension of the manifold. But the important thing is we have this part, and this is essentially the inside, if you like. So maybe I'll put this in red. So there is maybe this part here, and that would really correspond on this picture in this illustration to the inside. So we can now again ask the question, what if something falls into the black hole? And now we can draw a world line, and it turns out the world line looks like this. So we have a much larger fraction of the world line in this diagram. We see in particular how the world line enters here into the part inside the event horizon and approaches the singularity. This is actually a real singularity. Here it's not only the chart map that is bad. Here we have a singularity in the sense that the real curvature, the thing on the left, is actually diverging. But the whole point is that of this thing is that if you want to describe in general relativity an object like a black hole, a lot depends on a clever choice of the chart maps. And one of Roger Penrose's big contributions was actually to realize which maps give us a good and complete picture of what's going on in objects such as black holes. And this, what you see here, is actually something that is today also called a Penrose diagram. And it's just, you could see it as a very clever choice of coordinates that is suitable to understand much more than we can with these, let's say, trivial coordinates or much more obvious coordinates from a far away observer, but actually not very adapted coordinates to describe this region. And let me briefly switch to another document. This is the document that you can find on the web, which was published today, which describes essentially on a scientific level why this Nobel Prize was given. It's actually a very interesting document, and at least after this course, you will understand much more than is actually stated in this document. But let me just say one, or maybe not, make you aware of two things. One is this so-called Schwarzschild Metric. This is something we'll learn in a month or so, and that is essentially how, I mean, we haven't yet introduced the metric on manifolds, but that will be the central object that describes the geometry of space-time as created or as induced by a black hole. Then the other thing I wanted to show is that indeed you find here diagrams, and this is now also a Penrose diagram. It's a little bit more complicated compared to that one, because what this diagram does, it also explains not only what is called an eternal black hole, one that was always there, it actually explains how a black hole forms. So you see here again this singularity, but this thing is somehow matter that falls into the black hole. So it's a star that collapses. And here is really the contribution of Penrose that led to the Nobel Prize. It was namely unclear before his discovery or before his theoretical reasoning whether black holes could actually form. So there was this so-called Schwarzschild solution that I mentioned before, but this was a highly symmetric solution. So one could essentially show that a black hole with perfect symmetry could exist. But the question was, could a black hole form in a situation where we don't have perfect symmetry, with real matter that is, of course, not very symmetric? I mean, the Earth is not perfectly symmetric. If it collapses, or if the sun collapses, could it in principle form a black hole? I mean, in this particular case, the mass would be too small, but if the sun was larger, could it form a black hole? And Penrose managed to show, not least because of these diagrams, or using such representations, that indeed black holes can form even if you don't have perfect symmetry. So essentially, his main contribution was to show theoretically that a valid solution of the Einstein field equations that we will also see is the formation of a black hole. And then I just mentioned that, and we'll also maybe come back to that later in the course. Of course, black holes could then also be discovered experimentally, and that was the other part. That is now the other part of the Nobel Prize, the confirmation, essentially the experimental confirmation that they exist, for example, at the center of our galaxy. Okay, that was a small intro, essentially based on the latest breaking news. And yes, if there are any questions regarding that, I guess most of the deeper questions will be answered in the course of this whole course. I mean, you have to wait maybe a few weeks, but I'm happy to take questions already now. Okay, there seem to be no immediate questions. I'm sure there will be many questions once we treat these diagrams in more detail. It will be quite fun to actually reflect about what happens if you have this word line entering this event horizon and going towards the singularity, and reason about what that means. And we will also see that this poses problems in modern physics, because these diagrams don't yet incorporate the possibility that black holes again radiate. This was then Hawking's discovery, that they can radiate, and when they radiated all their energy, they will disappear again. And then the question is also, what happened, for example, with everything that fell into it once the black hole disappeared? These are questions we will very briefly treat at the very end of the course, because I will try to give an outlook on future research or current research, and also mention some open problems. But now I'll go back to our technical discussion, and we are actually in the middle of developing tools that allow us to work with these diagrams. And in particular, what we are doing is actually to understand in different representations what, for example, a word line could mean. So you see here a word line in this diagram, and you see one in this diagram. And we have already learned that vectors could be understood as somehow directions of such curves, of such word lines. And now a specific question you could ask is, if you know how the vector looks like here, how does it look like here in the other diagram? And this has to do a lot with the concept we just introduced, which is the concept of, or actually which I announced I will introduce, which is the concept of push forward and pullback. So this is exactly about how do we transform these objects from one here in representation to the other, or more precisely in a diffeomorphism from one manifold to another. That's the more general thing. So let's now return to these more mathematical things. So we still need to develop that language, and now I hope you have enough motivation to learn that language to be able to actually talk about these exciting objects that we have really in the universe. And nowadays we know we even have photographs of them. Okay, so the chapter we are in is now push forward and pull back. And maybe I'll just split that. Let me first just talk about the push forward. And the push forward is push forward of a vector, to be more precise. So what do I mean by that? Now I no longer draw I'm not very good at drawing, so I will not attempt to draw the real black hole, but this should stand for some real manifold. And then there is maybe another one here. And let's call this manifold here M, and this one here N. Now, vectors don't live on the manifold. Vectors live in the tangent space to a point of the manifold. So let's look at the point. And then there is, of course, a tangent space at that point, which we gave the name TPM. Now, if I have a diffeomorphism between the two manifolds, phi, so diffeomorphism is just a map from M to N that is invertible and that is differentiable in both directions. And for the moment, think of differentiable as being infinitely often differentiable. So it's a smooth map from one manifold to the other, an invertible smooth map. So therefore, in particular, we have an image of that point under that map, phi of P. And then we have also a tangent space around the image of this point. This is now, of course, a tangent space not at P, but at phi of P of the manifold N. It's a completely different space. So notice that's a different space, but of course it has to have the same dimension because it's diffeomorphism, and therefore the dimension of the corresponding tangent spaces, they correspond to the dimension, by the way, of the manifold, will be the same. Now, the question we want to ask is, if we have a vector here, how is it somehow transformed into a vector here? So we call this vector maybe V of some curve gamma, and maybe I drop the P just to make the notation a bit less cumbersome, otherwise there's too much in the picture. So what do I mean by V of gamma? So what I imagine is that there's a curve that passes P, and this vector is essentially the velocity of that curve. We have defined that, what that means. So this is the curve gamma. And let's just assume, as always, that the curve is parameterized in such a way that at parameter value 0, we pass the point P. This will just simplify our life. That's not otherwise of any importance. Now, of course, there is an image of this curve. Maybe I draw it here. That's what's the image of the curve? The image of the curve is the curve given by gamma and then phi after gamma. That's what I call the image of the curve. It's naturally a curve on the manifold N. Now I already gave the motivation last time of this push forward. So the push forward is a map from the tangent space TPN to the tangent space T phi P of N. And this, so let me write this here again, because this is important to realize where does this map start and where is the target. So that's the target of the manifold. And now the question is, how is it defined? And the definition is obvious from the picture. So I will, by the way, in the following often, I mean, we now have essentially introduced the basic concept with a quite deep level of rigor. I will now often only draw diagrams, but in the lecture notes, everything is still given with the full rigor. So I will not, I'm not less rigorous. I'm just not writing everything that I could in principle write in order to also increase a bit the speed, because otherwise we will not arrive where we want. And of course, this lecture is not only about differential geometry, but you should still, I mean, there's the whole, in the back, there's all the rigor, and you can read this whole rigor if you like, and you should do it. I mean, I encourage you to actually do that. But so what the picture tells you is that this new vector here, what it should be is just the new velocity vector of, or the velocity vector. So this vector here should be the velocity vector of the image of the curve. So in our terminology, in our notation, it means that this vector here should be V, not of gamma, but of phi after gamma. That's the image of the curve, of course, at the point phi of P. So if I write this here out, so we have V of gamma at P is mapped to V at phi of, I just write it here again to have the full thing. This is essentially the definition, if you like. It's now phi after gamma at phi of P. That's what this mapping does. So, okay. Now, this mathematically, that's not, I mean, this is intuitively the thing, the way you should think about the push forward. It just is the very natural, and let's say, the most natural thing you could do with a vector on this space if you want to map it to this space. Just take the curve corresponding to the vector and look at the image of the curve. But mathematically, this is a bit cumbersome to always look at the actual curve and so on. So it would be more useful to have a kind of more direct expression for that. And in order to arrive at that, we do our usual trick and say that, and remember what a vector is. A vector is a map, is mathematically something, an object that acts on a function, on a C infinity function. It acts on a function defined on the manifold, and we just let now this vector act on a function. So we take the push forward of a vector. So let's take this. So the vector is originally V gamma P, and now we apply the push forward to it. And now I have a new vector. So this object that I just defined is now already an object in T phi of P of N. And to understand what this object does, I take the whole object, let me put the bracket around it just to make clear it's now one big object, and I apply it to some function G, or to any function G. So this should be true for any function P. And now I just apply the definition. So we, of course, know what that is. We just defined it. So let me write down the definitions. By the definition, V of phi after gamma evaluated at phi of P. And this, of course, is still applied to G. So far, I didn't do anything except for applying the definition. And now I again apply just the definition, namely the definition of what a velocity vector is. Now you have to remember 1 week back, and the velocity vector is defined as evaluate the function at the positions where the curve goes through, and the curve is, of course, now this curve. That's the curve here in the vector. So we evaluate the function at the curve and take the derivative and evaluate the whole thing at the parameter value 0, which is the parameter value where the curve passes the point of interest. Now, what I can, of course, do is to exploit the fact that composition of functions is associative. So I can just re-bracket the whole thing, or I wouldn't have needed any brackets, but this is essentially to emphasize the other steps. And now I go back and say, this is now just a curve gamma applied to a new function. So I can again look at the velocity, or define this in terms of a velocity vector, but the velocity vector is now applied to G phi. I hope you see that, again, I just applied the definition of what V means, but now I grouped things differently. I now regard this as the function the vector acts on. So because this is true for any vector, and you see, if I look at this thing, here is just any vector of TPN. Of course, I wrote it as a velocity vector, but I could now also write it in a different way. I could say, let's take any vector of TPM, and now the push forward of this vector, I essentially just copy what I've written there. The push forward of the vector and the whole thing applied to G. Okay, maybe I put again all these brackets, is the same as taking the vector and applying it to G after phi. And this is again very intuitive if you look at the picture. So let me maybe make sure you can actually see the pictures at the same time. And so I'll just open this a second time as usual, just a moment. Okay, now you still can see here the picture. And what this formula that we just derived tells us is that the push forward of a vector applied to G, so the push forward of a vector lives here, this thing, is the same as applying the original vector to the function G after phi. G after phi is, of course, a function defined on this manifold because it starts with phi. And so that's again very intuitive. It again reflects the fact that we just did the most natural thing to transform a vector into that. And this definition is very useful. That's something you should remember. There are a few things where I will tell you, please remember that, or try to maybe make a list of stuff, maybe a short summary of things you should always remember. And one of them was, by the way, the definition of this velocity. That's something you should always remember. And this formula for the push forward is also something that should be on that list. There are not too many things. Maybe you can fill in one A4 paper with these things if you write small enough, but it's not an infinite number of little results that you need to learn. But that's, as always, the nice thing about any mathematical theory, that there are relatively few important things you really need to remember. Now we have done the push forward, and of course, as always, you should just interrupt me if there are questions. Otherwise, I will just proceed to the next very small subsection, which is an extremely small subsection. But if you have now pushed forward a vector from this space to that space, there's also a pullback. So we can also go the other direction. But now, by the way, I will, okay, before I said phi is a diffeomorphism, actually all I said is true, even if phi is just a differentiable mapping in one direction. Later I will again assume it's diffeomorphism, but to be fully general, you could even, for this part of, let's say, until in 2 minutes or so, always assume this is only differentiable and only goes in one direction. So whatever I said is true. And for arbitrary maps, So this could be a much lower dimensional manifold, and we still have this definition here. Okay, now if this manifold is not a diffeomorphism, then I can only push forward vectors from here to here, and I cannot get a vector back from here to here. This is also very intuitive, because if this is a lower dimensional manifold, then if you want to push back the vector, it's not uniquely defined, because there are several vectors here that give rise to the same direction here if this is lower dimensional. But for covectors, so a covector is an element of the dual space of T star Pm. For them, it's exactly the opposite. So we will define a pullback, and the pullback has the star upstairs. And this is now a map from T star phi of P. So it starts from the lower one, but it doesn't start from the tangent space, but from the cotangent space that I introduced last time. And it goes to T star at P of M. And so let W be any element of this cotangent space. Then, of course, I will call the image of this phi star W. And I haven't said much of that. That's just notation. Now I need to tell you what is phi star W. To say what that is, I need to remember how I can make statements about covectors. So, of course, as from what we have seen, I've just written, this is an element of the covector space, and the covector acts on a vector by definition. So it's a good idea to let it act on an arbitrary vector V. So V is for the moment, again, an arbitrary vector as before. And now we just define this to be omega applied to the push forward of that vector. So by the way, one often omits brackets. I could have put brackets here around V, but you see there are always many brackets, and so one tries to omit them whenever it's not absolutely necessary. And here it's clear that this is just something acting on V, so I don't put the bracket. And this is essentially the only object that you can naturally define. So when you have already defined the pullback, the push forward, then the pullback is essentially the thing that is, this is the only thing that is in a way compatible with the push forward. So it's compatible in a way that, yeah, we will just see once we now generalize that to tensors. So that's all in this little, I said it's a very small section or subsection about the pullback. That's what the pullback is. So it just, instead of evaluating the covector on this thing, on a vector given here, it essentially takes, I mean, yeah, or instead of, so the question is essentially here, how does this act on a vector on M? So the pullback, how does it act on here? You just, what you do is you move the vector to here and then just apply the W. Okay. Now, from now on, we really have to assume that this map here is a diffeomorphism. Otherwise, what I'm now going to tell you doesn't make sense. What we're now doing is the push forward, or let me just do the pullback. The push forward is then obvious if you see that, because it's just the other direction. The pullback of a tensor, of tensors. So now, just to stress that I write here, phi really needs to be now a diffeomorphism, no longer only differentiable. And let me just, again, in the lecture notes, there's the general case, but let me just do one example. But the example is general enough so that you can immediately see how this works for a general tensor. So let's consider, however, a 1-1 tensor on T. So it's pullback. So I start from the lower one, from T phi of Pn. And now I want to define the object defined by pulling back the whole tensor. And now it's always somehow the same trick. To understand a tensor, I have to feed the tensor with its arguments. So first of all, this is now a pulled back tensor. So I want this tensor to be a tensor on TPM, because that's the pullback one. This one was, of course, this was already written. The original one was on T Pn, or t phi of Pn. And the trick is always to feed it with its arguments. So because it lives on Tpn, it takes as arguments elements that live in Tpm or Tp star m. And because it's a 1-1 tensor, it takes one covector and one vector. So this has to be now in Tp star m, and this has to be in Tpm. And now I just have to say, what should that be? So now I have to give the definition. And you probably can already guess. In these definitions, one always does the obvious thing. So the only thing we can do is to somehow evaluate the tensor. But we already know how, so this tensor will now be on on the n manifold, on the tangent spaces to n, but we already know how to move these objects, a covector and a vector, between these two spaces. So what we do is we just move W, which is an element of Tp star n, to be an element of Tp star n. But now we are in slight trouble, because when you look here on our previous thing, what we did is the pullback of a covector went from n to m. But now we want to go from m to n. But here it's now, of course, important that I've written here, it's a diffeomorphism. I can just turn things around. And if I take the pullback of the inverse of phi, then, of course, I have a map from Tpm back to T phi Pn. And so what I'm doing, therefore, is to write here phi to the -1, that's the inverse, star, the pullback of that of omega. So the pullback of the inverse is, again, like a push forward. It pushes towards n. And for the vector, we don't have this difficulty. For the vector, we directly have defined already a push forward. So we just apply this here. So that's the definition of how to move tensors around. I'm aware of the fact that this is all appears quite technical and a lot of notation. Again, the only thing I can do is to really encourage you, or to tell you, and you have to believe me, that it's worth learning this notation. Because only then we can, in a precise manner, talk about all the actually real interesting things. Because you see, when we have this diagram at the end, we cannot talk about this. This is just beyond our imagination as an object. But we can talk about diagrams like that. That's what we can do. We can draw them on a piece of paper and reason about them. But in order, a diagram is essentially a language. And what we are doing is, in a way, develop this language. And to learn a language is sometimes or oftentimes quite painful, but once you master it, it will, maybe unlike a normal language, in this case, it will really open a completely new area where you can understand things. I'm not sure this is also true for normal languages. Maybe it is. That's what my language teachers kept telling me, but it's certainly true for this language here. Okay, now we need the next element in our language, which is something that you have certainly already heard of, namely vector and tensor fields. And indeed, these are not different things from what you have heard. You have certainly in electrodynamics heard of vector fields. You must have heard that. And maybe also of tensor fields. The only thing that is new here is that we will now, unlike in electrodynamics, not consider only fields on R4, on the four-dimensional flat space-time. The big difference is that there will be fields on an arbitrary manifold, in particular one that is curved, and in particular geometries, again, like this. So in order to, I mean, here you can, this is not flat space-time, so whatever you learned about tensor and vector fields would not immediately apply there. We have to redefine these concepts for curved spaces, and curved spaces abstractly are our manifolds. Now, here in this chapter, even more, I have to skip many technical proofs, and I will just make the statements, and you have to believe me that these statements are true, or read them up in the lecture notes, or read the proofs there. Now, what is I mean, maybe I'd first give an intuitive picture of what a vector field is. And I mean, the most, let's say, let's say the most direct thing you should think of is that you just assign now a vector to any point of the manifold. That's a vector field. I mean, before we always had these pictures here where we had one particular TPM and we had one vector, but this was just for one point. And the only thing we now do more, which sounds almost trivial, is to say, let's now not only do this at one point, but let's do it at every point. I mean, if you are for the moment not thinking of space-time, but just of normal space on Earth, a vector field would really be not only an arrow somewhere. So actually this time I have an arrow here. So there's this signpost out of my house, and this is an arrow. Actually, it's in the house, but this is an arrow standing there and it has a fixed direction. Now, I could imagine I just such arrows everywhere distributed on the Earth's surface. That's a vector field. Now, what's the difficulty? Why are we not done? Why am I not done by telling you that? The problem is that when you look at these tangent spaces, the different tangent spaces at different points have essentially nothing to do with each other. I mean, even on Earth's surface, I could have a tangent space here where I stand now, and there's one maybe in Australia, which is of course just almost upside down. And how can I somehow connect a vector here to the one there? You could now ask, why should I connect anything? So actually, I don't want to do that, but at least what I want to know, and this will be important, is to see if I just move a little bit, if I move here, maybe by 10 meters, then I would say still the vector there should be comparable to the vector I had before. I mean, for example, if I had the signpost here and there was 1 meter apart, then there should be a notion or a way for me to tell, is this sign, or let's suppose I have here this pen and here the signpost, but there are different places. Pen is here, the signpost is here. So they are, technically speaking, in two different tangent spaces. Nevertheless, it makes, of course, sense to say that these two have now the same direction. But mathematically, how do I say that? Because they're just living in different spaces. So I need a notion to somehow compare this thing, this arrow here, to the pen. So I need to somehow have a natural way to bring them together. And that will cost us some work to do that on a technical level. That's a non-trivial thing to do. And it's not only non-trivial for some, let's say, technical reasons that you can forget. It's even at the end, it will be the essence of understanding the geometry of space-time. Because what you will see is, of course, it will not always, so what you will see, maybe just as an outlook, and to make clear to you that this is not just a mathematical subtlety, it's really a physical thing. We will see that how we compare things actually depends on, for example, how we move. So if I want to compare this to that, I somehow need to move from here to here. I take this thing, walk from here to here, and or maybe I better take the pen, walk from here to here and look, is it the same as the signpost? But I could have walked directly here, or I could have made a detour, maybe a bit forward and backward, and arrived here. And what you will see is that if the manifold is curved, actually if we did it on the real Earth surface and measured very precisely, the answer would depend on the path. If I moved from here to here, I may find that they have the same direction. If I moved via whatever, some remote place, via Vienna, and came back, always keeping it straight in the same direction, it may no longer fit. And that's a sign, that's a consequence of the fact that the Earth's surface is actually curved. And so these techniques that we are now going to develop will be essential to essentially quantify the curvature of space or of space-time. In relativity, of course, we will talk about curvature not only of space, but of space-time. But it's always good to imagine or to think about the Earth's surface as a kind of example, which essentially is on the mathematical level exactly the same. Okay, so this big chapter, I will just now very briefly start, and then we make a small break. So the first thing we will now introduce is the so-called tangent bundle. Okay, that's a mathematics word, and mathematicians have even more general terms. They talk about fiber bundles, and I will maybe after the break make a small diagram to explain to you what these are. even in the more general context. But essentially what we are talking about when we talk about the tangent space is Tm. That's a new symbol we introduced. So the only difference to the previous one, it has no P. And what we mean is just the disjoint union of all TPMs. And I emphasize the word disjoint because for different P's, the element, these are just completely different sets. So they, so this square union stands here for disjoint union. Now, probably intuitively, it's clear what that should be. It's just you take any tangent space that I've defined at any possible point. And now the first, let's say, thing you should realize is that an object in this space Tn is an object that has 2D, that is expressed by 2D real numbers instead of only D, if D is the dimension of the manifold. Why is that so? So maybe just write this because that's the first thing you should really think about. Every element of Tm is specified by, first of all, I need to give a point. So because I have the union of all TPMs for all P, so I need to say, where is it? And then I need to still give, now I have identified which TPM we are talking about, and then I still need to give the vector VPM. And of course, to specify the point, we know in coordinates, we need usually D coordinates. I mean, that's by definition what it means to have a D-dimensional manifold, that we need D coordinates to specify a point, and then to define a vector because the tangent space, because that's an element, of course, of TPM, that requires again D components or coefficients, if you maybe write coefficients, if I write the vector in terms of a basis. So in total, an element of this new object we defined is specified by a place, which is with the coordinates, and by a direction. So this is, in a way, if you think again about the arrow, before I was just talking about the direction this arrow has, now I'm including in the description the position where it stands. Okay, that all sounds now still simple. Now I will have to draw a quite complicated diagram to introduce all the terminology we will need, but probably it's better to do that after the break. It's already time for the break. So I'll stop here for a moment and I will continue again at 5. And of course, in the meantime, I'm very happy to take questions. Okay, are there questions? Eleanor, was there anything in the chat that I should answer?
I haven't seen anything in the chat.
Okay, well, that's good. Then I'll just wait here, and whenever you have something, then please ask. And otherwise, everyone should maybe return around 5, or let's say 5 sharp. I start again. By the way, just as a remark for those who usually stay during the break, in the recordings, the recording usually includes the break. And so if people would wish that if they ask questions during the break that this is not recorded, I could, of course, change that scheme. So if you would prefer that, then maybe just drop me a line later and tell me that you prefer recordings without the break. Maybe this gives more motivation then to ask questions if you're unsure whether they're good questions and don't want them to be recorded forever.
So actually, I have a question
Yes.
concerning the last lecture.
Yes.
If you look at the last maybe PDF, last slide, And you
Yes,
give
so
that.
let me briefly switch to that one. So I guess it's the one from the 1st of October.
Yes, and above that, you gave the transformation for a tensor.
Yes.
I think something is wrong in this transformation. Actually, many things are kind of wrong.
Okay, that's bad for me.
So,
okay.
First of all, the x over the xj over the xs should be delta js. So this cannot be here in this notation.
So
it should be probably.
So you're talking about this expression here?
Yes, exactly.
Okay, yes. Okay, whenever I'm dealing with indices, there's a high risk I'm making lots of mistakes. So you're saying now there are many. So where is your first mistake?
So first of all, it shouldn't be the x over the x. It should be probably the x over the y.
Yes, right. Here should be, of course. Yes, you're absolutely right. So let me correct that. So by the way, let me also immediately give the rule of how to determine whether there should be an x or y. Just for those who listen and want to. So these m's here, they belong to a tensor component defined with respect to y. So that's why, I mean, this is of course now not the reason, but that's a way to remember. That's why wherever you have an index n, it should be somehow connected to a y. Now, the same is true for the n, and that's why you're, of course, absolutely right that, let me put that in orange because it's correction, or maybe even in red. So that should be a y here, and of course here, because these things belong to the y. So yes, okay.
Then second, obviously there are indexes wrong, probably, because whatever is I should be J or opposite. Yeah. So if you look, what is the upper index on the tensor? Yeah, it's I, but I is downstairs in the.
No, this is actually.
This is right, because this is summation. Yes,
because you do a summation. Yes.
Yes, this is right.
By the way, the other rule that maybe everyone should remember that if you have an index appearing twice, and then it has to be the case that one is upstairs and the other downstairs, except if you're doing something basis dependent. If you're deliberately doing something which is only true in a basis, which one may sometimes do, and maybe we'll see examples of that, then this rule might be violated. But we're trying not to do that. So actually, it's a good consistency check whenever you do something and don't want to do something basis dependent, which you shouldn't, because I told you this is then usually not, I mean, it's then no longer obvious whether it's physical. It should be like that. So for example, this I, because it's downstairs, should appear here upstairs.
Also, I have a maybe general question.
But there are no other mistakes in that, because you said
that's right now fine. I thought that the indexes are wrong, but they are fine. You're right, absolutely here. So the one things I have the problem with is just general notation. If you go, for example, to your let's say your notes, and let's say let's look at this.
Open the notes, yes. So you mean the lecture notes?
Lecture notes, yes.
Okay.
And let's look at the formula, let's say like 25. Yeah, this is about the relation between basis and the inverse matrix.
Okay, I hope I have the same version, because I sometimes update things and then the numbering may in principle change. Is it, you're now talking about?
Yeah, that doesn't matter which, yeah. So my question about this notation is, you have this rule here in which, you know, J and I somehow are separated by space, and I'm not sure what is the relevance of it. For example,
yes, that's a good question. So you are essentially asking why is here, for example, the K and then the I is somehow
here, for example, not the opposite. Yeah, why they are not opposite, and what would be the meaning if they are opposite? Yeah.
Yes. Okay. Yes, that's a very good question. So let me first of all say that if when we are talking about tensors, which we didn't do here, but that's why I generally use that thing. And maybe, okay, let me just write into these notes here. So remember what a tensor is. Of course, it takes as arguments covectors and vectors. So for example, a tensor could take some omega and then maybe a vector, maybe some vector x and another vector y. Now, if I now write the components of this tensor, then I usually have a component which is first a component corresponding to somehow this first argument.
Mm-hmm.
And that's kind of a contravariant part. So this will be an index upstairs. So I will have, maybe I use even a color code. So let me here rewrite this with different colors. So let's just make the first argument blue, and then the other one, let's say orange, so x and y. Now, if I want to use indices, I will, because it's a 1-2 tensor, I will have one index upstairs, and I will have two indices downstairs, j and k. And now you probably already see why I left here a space.
Yes.
In principle, I could have another tensor, which is, okay, let me just make this in another color or in gray, because something like, I could have, I mean, we haven't written it usually in that way, but I could have written this as the tensor. It's a valid tensor. Usually we just ordered things that first we have all the contravariant things and then the covariant ones. Or I could even have changed, let's say, just the covariant part. So I could have had a tensor yx. This is another one. So let me put here a tilde, and then this would be defined as the opposite of that one, so to speak. So this, first of all, tells you the order in which I give the arguments actually matters, because that's really a different tensor than that one. Because the second argument is here treated as was the third here, and so on. And in order to keep that order also in the component writings, I always really want to be sure that the order is maintained. So I know that I is first, then comes the j, and then the k. I could have dropped that and just introduced the convention that implicitly the upstairs ones are always first before the lower ones. But this turns out not to be very convenient for later, because later we will sometimes have the need to turn one of the arguments from a contravariant one into a covariant one. We haven't done this yet. We haven't even the means to do that, but we will later do that. We want to raise and lower indices. And then yes, it would be cumbersome to have this rule, because by lowering an index, it would change the position where it appears. So I'm working with essentially with the assumption that in principle, it would be allowed to have a tensor which first takes, for example, the x and the y's and then the w. This would be again another one. And that the components of that t bar would then be something like I, j, or okay, maybe I to have the same as before. It would be something like j, k, I. I would then write it like that. So it's kind of, and you see, the notation always also helps to avoid mistakes. And in principle, I could somehow introduce definitions that allows me to move everything to the left and keep in mind that the upstairs are always first. But somehow it's an additional very good consistency check, and it's also useful for later when we raise and lower indices. So that's essentially the reason why I always choose a notation where the indices are not on top of each other, but have a clear order. Now, yes, in this particular case, it wouldn't, strictly speaking, have been necessary, because here it's probably well defined. I don't need that order because I never introduced gamma as a tensor in that way, but I still, just for consistency, do that everywhere.
But
I would, of course, interpret the gamma as a tensor.
The question is, doesn't really matter for this gamma, particular for this gamma.
In this particular case, it wouldn't matter because I only have one upstairs and one downstairs, and then somehow from that position everything is clear. So in general, if I mean, you could say that whenever I only work with one tensors, and in addition I don't lower and raise indices, so I don't apply this musical B or sharp map that we introduced at some point, then I could just live with a convention where I put all indices on the left and don't mind the order because it's already well defined what they do. That's absolutely right. But I don't want to distinguish the cases where I can do it and when I can do not, where I cannot do it. I just, kind of take the more careful position and always order them. But you're right that in this particular case, I would, I could do it without the ordering.
Okay. So one more quick last question. If,
yes, sure, yes.
If it's possible. So if
yes.
you say define this reverse of gamma -1.
Mm-hmm.
Now, if you multiply by matrix gamma, does it really matter which way the summation go, or doesn't matter at all? Which means you can summate, let's say, lower index of gamma -1 with upper of gamma, or opposite. So does it matter?
Yeah, you mean, okay, if I understand correctly, your question is if I put lambda ij and then somehow lambda to the -1 j k, this would give me delta ij. And now you're saying I could have done it in the opposite way and somehow.
Exactly.
Yes, this doesn't matter, but the reason why it doesn't matter is actually the following a priori not trivial fact that if you take normal linear algebra and just look at two matrices, it's one matrix, then it's not a priori clear that the same matrix that I call m to the -1 satisfies this and this. So in principle, there is a proof to be done because that this is the identity is a different statement a priori than that this is an identity. But then, of course, we know from linear algebra, from the usual, this is easy to verify that indeed, if I have a matrix if I found an inverse that satisfies this, then also it satisfies this. But that's something that is not immediately clear, that you have to essentially go into a small calculation to verify it. But at the end, the answer is yes, it doesn't matter in this case because the inverse has this property. That's essentially the reason why it doesn't matter. This is a fact about matrix multiplication.
Okay. Thank you
so much.
Does
this answer your question?
Yes, absolutely.
Okay. Okay, thanks a lot for the question. So, you shouldn't apologize for the questions, or as I said, I really encourage questions, and I'm very happy if this encouragement actually arrives on your side and you indeed ask questions. So now, as I hope everyone is back, are there other general questions you would like me to answer about the first hour of today's lecture? Otherwise, I would then just continue with this diagram or this more complicated picture that I just announced before the break. Okay, don't see any questions. Okay. The figure that I want to draw is the following.
Das ist eine Vorlesung.
I think someone is...
Die Podcast mit der Kamera zum Filmen und so. Die Mastervorlesung. Schuhe müssen dem immer muss umschalten.
Okay, so let me continue. I have a diagram where I first of all just draw the manifold M. And now what I will do is to essentially say that the Tm that I defined is in a way also a manifold, a more complicated one. So far I haven't introduced it as a manifold, but suppose this is a d-dimensional manifold, and I just told you this object here Tm is somehow a 2D dimensional object. It has 2D coordinates. So I can think of it as a new manifold, which is, however, no longer d-dimensional, but 2D dimensional. And it's the manifold consisting essentially of these objects, of an object that have a position and a vector. And that's itself a manifold. This is maybe, if you see it, this is again one of these things, if you see it for the first time, it's slightly strange, but you will certainly very quickly get used to it. So this manifold, the picture is it's more complicated, and it has all these tangent spaces everywhere at any point, and it consists of arrows at certain points. Whereas the manifold, let me draw maybe the objects within the manifold in green. So these are the objects, and here in this picture, this is just a picture. Everything on the left-hand side is kind of not really precise. That's the whole point of having maps. To really talk about things, we need the charts. But in the top one, we just have the elements of the original manifold. Now, as I said, we need charts to talk about this in a more precise manner. And what you're saying is that every element of this object can be mapped via a chart. And now I make the chart more explicit. The chart consists of d coordinate maps, which are all functions into the real. And let me here draw just one of the coordinates. Of course, the chart has d dimensions, but I'll just draw, okay, I guess you know it's a chart. I'm not writing this, but this point has now an image here. And on this axis here, it's xi of p. And of course, so I'm only drawing one, but there are d such dimensions. So think of this d-dimensional representation. Now the Tm has kind of twice as many dimensions. And I draw this now pictorially by a two-dimensional thing, because before it was just one dimension. So here an object is an object which has, first of all, coordinates, a coordinate xi of p. And this is the point where the vector belongs to. So here are some vectors, Vp, but then it also has the actual components of the vector. So this is this direction, and a component of a vector I can extract by applying this function dxi. So remember, dxi is the function that gives back the coordinate of a vector with respect to the a given basis that is defined in terms of the coordinates or in terms of the chart. So what this object here means is this is the ith component of the vector Vp with respect to the basis of the tangent space that is induced by the chart map X. So this was the chart map. So now I can see this as a new chart. I mean, so far I haven't, as I mentioned before, this is here the manifold, and then I want to see this as well as a manifold. And in order to view this as a manifold, I do it via telling you what the chart maps are. Because remember, a manifold is essentially just defined via its atlas, and the atlas is just a collection of all chart maps. So what I'm telling you now is that I define a new manifold Tm, or the manifold structure of it. So far, I just defined it essentially as a collection of points. It was just a union, but it didn't have any structure. But now I'm giving you the manifold structure by telling you what the chart map should be. So the chart map is this one. It extracts the coordinates of the point, and this is this part, and it extracts the components of the vector at that point. And now it's clear that this is, this is now a confirmation. It's indeed a 2D dimensional manifold, because I've now constructed a chart map that has 2D components, so 2D numbers that are in this chart. Okay, that's now on the pictorial level. On the mathematical level, I would now need to prove that what I wrote here is indeed a valid chart. And in addition, I have to show that it's a valid atlas. It covers the whole manifold. This is done in the lecture notes. And let me just say what one has to do on a, let's say, proof sketch level. And there it's really done. So what one has to do is the following. So all maps of this form should constitute an atlas, which means they should cover all of Tn. that this is the fact is clear, because here by definition M is already a manifold, so all charts X together will cover the whole manifold. That is the definition of what an atlas does. So we assume we already have an atlas for M, so we have sufficiently many charts that all of M is covered. But of course, if all of M is covered, this means that all points of Tm are covered, and clearly the dx just extract the components of the vector. So in other words, for a given, so if this is defined on a particular set U, particular chart domain U, then this map here is defined on essentially the same U and all vector spaces that are at points in this set U. And of course, if I now have the statement that all U, union of all U's gives M, then all unions of this U also gives M, and therefore I've covered the whole Tm, because the Tm is just the union of all Tpms. That's just this proof sketch. So as I said, I'm here only giving you the words, but the explicit statement is in the notes. The other thing I need to show is that this map should be actually an invertible map. So if I have now coordinates given, I should in a unique way go back here. And this can just very easily be given. You have essentially the point given in coordinates, and you have the components of the vector. So it's easy to construct the vector. Then the other important thing I need to show is I also want this new manifold Tm to be a differentiable manifold. And for this to be a differentiable manifold, remember the condition is that the chart transition maps have to be differentiable. So what I have to do is to look at two such charts, which I can construct by taking two charts here, an X and the Y chart, and this induces two new charts here, or two charts here, and then I just explicitly write down the chart transition map. This is a lot to write. This is written in the lecture notes, and then one can verify explicitly that if the chart transition map of M is differentiable, then the same is true for the chart transition map here. And this proves that this object equipped with the atlas defined in that way is a valid differentiable manifold. So we have now a new manifold, namely the manifold of essentially of vectors on a given manifold M. So we started with manifold M, and now we define a new manifold that contains all vectors. It's the manifold of all arrows, if you like. Now it just gives you some terminology so that if you read, I mean, you should, after this course, be able to read literature about general relativity, and sometimes this literature is quite mathematical. And there are lots of terms connected to what I just told you. And I'll just mention this term so that you can later match this literature to what you have seen here. So one thing that is usually done in mathematics is this is defined on a more general level. And one usually says one starts from a manifold, and this manifold from which one starts is called the base manifold. And then the new manifold that, I mean, the one I constructed here would usually be called the total space. And the other one is maybe called the base space rather than space manifold, but it's of course a manifold. Base space. This is just terminology. And then there is also a natural map induced from here to here, namely the projection map pi. What this projection map does, it just takes a vector here, and the vector has a location P, and it just extracts the location and tells you, this vector was at the point P. Of course, that's just essentially this part of the information that you extract. And this is called the projection. And now you can, of course, invert the projection and ask yourself, what is everything mapping to a particular point? So I can look at pi to the -1 of a particular point P. So, I mean, usually when I look at the pre-image, I look at the preimage of a set, but here it's just a set only of one point. So what's all vectors? What's everything here that according to the projection maps to P? That's obviously just exactly the tangents that corresponds to the tangent space at P. And that's now, again, to tell you the mathematical phrasing of that, that's now called a fiber. And this term is used because one can do the very same construction in a more general sense, not only for tangent spaces, one can essentially do it if you have other vector spaces belonging to each point of the manifold. They don't need to be tangent spaces. And this is sometimes useful. We will, for the moment, only need tangent spaces. And then this term fiber is maybe a bit strange. But if you look at this more general definition, then the Tm would be called a fiber bundle. So essentially, and this terminology refers to the fact that at each point of the manifold, you have a fiber, namely the tangent space, and the bundle of all them is the total thing we are interested in. It's the set of all manifolds. Again, this terminology is maybe a bit strange in the context of relativity, I think, if you hear it for the first time, but it's just standard terminology that you need to know about, I guess. Now, the whole purpose of doing all that was to define a vector field. Now I can finally tell you what a vector field is in a more precise manner. I told you before, a vector field just associates a vector to any point of the manifold. I tell you what is the arrow at any point in space. And so you can see it in this picture as a map in the other direction than pi. So it takes any point and says, oh, at this point, the vector is that and that. So let me give a name to this map. Let's call it V. I'm aware of the fact that I used V often for vectors. Nevertheless, I use it here on purpose. I use the same name and you will see why. So V is now a map. Let me write it downstairs and here scroll a bit so that you still have the picture. V is a map from M to Tm, which has two properties such that, first of all, is you want that Vp is, of course, the vector that you associate to the point P should, of course, be a vector in Tpm. I mean, that's not, I mean, that's obvious in a way, but it's not clear from the general picture because it's just a map from M to Tm. And in principle, this map could just associate to a point P here, a vector in a tangent space of a different point. But of course, you don't want that. So you require that it's indeed in this point. Or mathematicians would say it's in the fiber, which is, of course, this defined as we just did it. It maps any point to the fiber corresponding to that point. So that's the first requirement. The second requirement, and that's important for us, is that V is differentiable. And actually, this second thing, which sounds very innocent, V is differentiable, was the reason why we had to equip Tm with a differentiable structure. So if I just left you at this point and said Tm is just a collection of all tangent spaces, then this whole word V is differentiable wouldn't make sense because I would go from a set M, from a manifold M, to another set which is not equipped with a differentiable structure. So I couldn't even say what differentiable means. So we had to essentially lift this Tm or promote it to be a differentiable manifold in order to be able to even say what differentiable means. And remember what differentiable means is that if you actually start from a chart representation of a point P, go to the point, then apply V and go back to the chart representation of what you got, then you have at the end, you end up with a map from here to here. And this map is now a map from RD to R2D, because this is two-dimensional, and this map has to be differentiable in the usual sense of differentiability on RD. But that's why, you see, we needed this representation and all that. So all this structure is needed. I didn't just do it for fun or to entertain you with mathematical details. This is really kind of quite central. But at the end, the intuition behind remains the same. A vector field just associates to every point a vector. But now we can, based on this differentiable structure, we'll be able to actually now say, how do vectors change as we move along a path? And that's only possible because of this. And that's a physics question. That's really a physics question to ask, how does something change? How does this arrow change? If I have many arrows and I move straight, do I suddenly see arrows in the other direction, or how did they change? Was it the same direction still? So we need the structure exactly to answer this question. Okay, now there's just as a remark, which I don't even now write down, almost everything that we defined so far in the last lecture and also in the first lecture today, I mean last week and in the first lecture today, was about things individual points. And of course, all these notions can be lifted to notions on Tm. So for example, the push forward we just have seen, we defined the push forward as a map. And if I go here back, the push forward was a map from, or maybe the pullback, I just see here, the pullback is a map from T phi of P to P T Pm. Now I can do this at any point and then replace this T star Pm just by T star M. So I can promote all these operations to operations that don't only act on one point, but on the whole manifold. So essentially the pullback would then not only pull back the vector in one tangent space, but all the vectors in all tangent spaces. And it's just defined pointwise. So what that means more mathematically is maybe the following. If, and this is just a remark for a moment, let's take the push forward. Sorry, the push forward has to start downstairs. So the push forward was this. Between two manifolds. And now I define, so this was until now. And now the new thing we will do is to see it as a map from Tm to Tn. And of course, it's still defined in the same way. So it's just pointwise. This took a point, a vector v at the point P and mapped the vector v at the point P to some other vector, which we called, of course, phi star applied to P. And now you see why I called the map itself v, because the vector field is really described by the map v. The map v is essentially a definition of a vector at any point. I mean, maybe you shouldn't even think of it as a map, because when you think about fields in electrodynamics, for example, you just thought about a vector at any point. But of course, I could have written it as a map from R3 to the vector spaces. So I map V to a new thing which is called V star V. And of course, it's just pointwise defined as that thing. So if you ask, now what does this thing mean? It means at the point P, the vector defined by this map is exactly that vector. We will see that many times more concretely if that was unclear. But I hope the intuition is clear that we can, every pointwise definition, promote to a general definition. Okay. Now, vector fields are so important that we will give a new, or even introduce a new symbol. Oh, I forgot to maybe conclude with another terminology that should also be given. In mathematics, that thing here, a vector field, is sometimes called a section or a cross-section. Again, this is just a name, and I just want to make sure you're not confused when you hear the name section and cannot match it to vector field. It really means, in it's kind of the more general thing. So it's the name given to any map of that type. It doesn't need to be here into tangent spaces, but a map which satisfies essentially these properties in the more general case where this is not necessarily TPM, but some arbitrary fiber. So in the context of fibers and fiber bundles, a vector field is called a section on this level of generality. I will not usually use that term, but I think it's useful to be aware of the term. Now, I will, however, use very often the following notation. Gamma of M, of Tm, will be the set of differentiable maps, or so the sections, what I just said, from M to Tm that have the property above. So essentially of differential, maybe I should just have in, I don't want to repeat myself, the set of such maps. I mean, by such, I mean, let's maybe make here a star or something so that you can refer to it. So then maybe the even better way to phrase this here would be a set of maps of the form star from M to N. So this is just notation. Now, apart from just introducing notation, I can now also add some mathematical structure. Maybe what I want to say is that this space, the space of all vector fields. So this is essentially the space of all vector fields. Maybe I'll write this down because that's important. So it's the space, serve some larger bracket. So this is, or not even a bracket, is the space of vector fields on N. And we will, of course, very often talk about vector fields. So we will very often see this symbol. And this space can be equipped with a natural addition and multiplication. And I call it S multiplication for scalar multiplication, because we will distinguish it from multiplication with a function. So I'm writing that really for this purpose. And what I mean by that is that if you take a vector field V, so let's take two vector fields, so two elements of this, and let's take a scalar, so a real number, then I can define what it means to add them and also to multiply them. So I just combine this. So I can do stuff like this. Take the vector field V and add S times the vector field W. And what it means is that evaluated at the point P, it's just the addition and multiplication of the corresponding vectors at that point. So it's a very natural operation. It just means I add and subtract and multiply vector fields by doing that point twice. But again, this is something that I'm not just telling for fun, because we will just see in a moment that we can also define a multiplication with a function. And it will be important to be aware of some subtleties that arise in this case. So that's the next thing. So we can also, that's a different thing, I should stress that, equip, it's a more general thing to do. We can equip this space with a multiplication. By equip, I mean we just define new operations with a function. So that's no longer an S multiplication, but a multiplication with a function. Namely a function from C infinity m. And again, it's extremely intuitive what you do. You take the function and multiply it with v. So what does this mean? It means point-wise, you just evaluate the function at the point p, and this gives you a real number, and then you take this real number and multiply it with the vector at the point p. So it's again extremely intuitive, but now you this multiplication with s was a multiplication where you multiplied each vector with the same real number. Here, you multiplied each vector, at each point you multiplied the vector potentially with a different number. And I will, at this point, the importance of this distinction may not be clear, but you will see examples where certain rules hold if we multiply vector field with a scalar, if we do an S multiplication, but the rules look more complicated or don't even hold if we multiply the vector with a so-called position-dependent number. That's why I'm stressing that particular point. Now there is a last thing, and there's a lot of notation, and now the notation may indeed become confusing if you're not always really thinking hard about where are these objects living, what type of objects are there. So for example, here you need to think about, oh, this is a function, and what does it mean to multiply a function with a vector field? Oh, it means the pointwise multiplication. And now there's a different thing I could do. We can also apply a vector field to a function f element of C's infinity m. So C infinity m is just the functions on the manifold. What do I mean by that? This is now not the multiplication, but it will be written almost in the same way. So I will actually, that's just for you to be attentive, we will write stuff like v f. And now this could really look like you multiply the function with the vector field. So it looks like this thing, but this is not f multiplied with v. That's a different thing. So that's just for you to be careful. But I didn't so far tell you what it is. So what is it? So if I say I apply it, I mean that I take a function. So v can be applied on a function and generates a new function, C infinity m. What does it do? So it takes the function, and as I said, the notation, the new function is called vf. Now, as usual, I need to tell you what is this now. So far, I just told you there is some new function. So what is this new function? This new function vf is a function on the manifold. So what it does, it takes as input a point p. And now I need to say what this value is. So this is now a real number. If the function is applied at the point, by definition of what C infinity means, that gives you a real value. And now I'm just saying, should just be the value I got if I applied the vector at the point P to the function f. Now you need to remember what that means. What does it mean to apply a vector in a particular tangent space belonging to a point P to a function? What it means is that you take the vector, which is a direction, and walk along the vector and see how the function changes as you walk along this vector. That's at least the intuition of what this means. So it's the derivative of the function f as you walk along a curve with direction v. So this is a well-defined number as well. So in other words, what it means to apply v to a function is you do that at every point. At every point in the manifold, you have now a vector defined. That's what the vector field does. And at every point in the manifold, you walk along the vector at that point. So there is here at point P this vector, and I walk along this vector and see how the function f changes. And that gives me a value at that point. So at the end, I have a value at every point. And that's by itself, again, a function, namely a C infinity m function. So everything is still differentiable, of course. That's the requirement that I I put into the function an infinitely differentiable function. And it follows from the fact that V is differentiable and that the input is differentiable, that this thing is again a differentiable function. I didn't show that here, but that's very easy to verify. Okay. Any questions about that?
Yes, I have a question.
Yes, please.
So you defined the vector fields and I think later also the tensor fields with this map. And you said it should be differentiable. So usually when we had maps, we said they were differentiable with respect to the charts to Rn, and in this case from Rn to 2Rn.
Yes.
But this would mean that we now imply like always differentiability is always associated with like a notion of addition or subtraction. So this would mean that we define on the tangent bundle an addition or a subtraction, which again would mean that we would in a way or another compare two vectors of two different tangent spaces. And now my question is shouldn't we be a bit more worried about like just comparing those two objects to those two fields?
So, actually, if you look at the addition, I mean, this is a very good point. We have to really be worried that we are not, so what we should actually make sure we are not adding two vectors of different tangent spaces. Now, indeed, if you think, so I'm not sure exactly where you refer to when you say that we have addition. Of course, in the whole notion of differentiability is of course built in a notion of subtracting things, because if I want to calculate the differential really at the end, we have to really evaluate the differential. We are subtracting, for example, two close by vectors. So, okay, let me make an example. If I have even not a vector, I have let's see. Yeah, so generally, if I have two vectors at two different places, and now I want to see how the vector changes, then indeed what it means is that I somehow compare these two vectors and I take the differential. So I will take one vector and then subtract the other one, which was in a different place, and then somehow divide that by some small number. And so this division that appears in the derivative, this is indeed a difference between vectors which are at close by but still different places. And that's actually the reason why this is allowed is, and we will later do that even in more detail, is that if you look at this chart representation, this really allows you to talk about like close by vectors, because if you take this chart representation here, let me maybe look at it here on the larger thing. So this is a chart representation of Tm, and if I look at 2 points here, let's suppose I take a point here and a point here. What do these points mean? These are actually two vectors at different places, because this point stands for a vector at with coordinate xi here, and this point stands for a vector at coordinates here. Now, and there are also different vectors here in this case. Now, talking about, if I now have, for example, a curve in this Tm, then this curve may pass through these two vectors. So there could be a curve like that. And I could now ask myself, for example, what's the change as I walk along this curve? And now by the change, I would really take the coordinates here and somehow compare it to that. And with that, I really compare two they are really different spaces because the coordinates are different. But because I have this representation and everything is now in R2D, this is well defined, because the subtraction in this representation means really the subtraction with respect to this R2D. So in that sense, the way this problem that you allude to is avoided is to really work in this 2D dimensional space where we have just a normal Euclidean structure. And you could even say that the way we equip this Tm with a differentiable structure is by requiring that we are allowed to do that. So in a way we impose that. A priori we would not be allowed to do it, but now we impose it. Now we will later come back to that because we will have to really see what does it mean when a vector changes from here to here, and we will actually devote the whole section to that. So maybe what I said wasn't now fully clear. This may become clearer in a week or so when we introduce something called connections on manifolds. But maybe the answer so far is really by going into these charts. And once we are in a chart, we are just in normal, let's say, multivariable analysis, and we can do everything that is defined there. And essentially why these charts, we are moving all the problems towards that. So all the differentiability refers to notions in these RD and R2D spaces, and there everything is well defined. What we have to worry about is whether these are now coordinate dependent notions, but as long as we are just talking about is it differentiable or not, because the chart transition maps are differentiable, the question whether something is differentiable or not doesn't depend on the chart, because we can in a differentiable way move from one chart to the other. Now, I'm not sure it actually answers your question, but maybe at least my answer gives you a hint where to ask more precisely.
Okay, so we assume that we can compare two vectors from different tangent spaces in this way, and that is like an axiom, and like all manifolds are smooth and so on.
Yeah, so we somehow impose it by really, so in a way you're absolutely right that we are a priori not allowed to do it. And then via requiring that this is actually the chart, a valid chart, and this is really the atlas, and we are now imposing the differential structure of this 2D space, which really allows us to at the same time change position and direction. That's what this 2D thing does. We can walk in any direction in this two-dimensional space. So this curve here changes at the same time the position as we walk in this direction and the direction, and we can now talk about this in one go and compare things. So we are somehow explicitly imposing that we are allowed to do it. But we will have to be careful in what it really means physically, because so far we haven't cared about what does this then mean, these changes. And we will define something, the covariant derivative, and there we have to be careful that whatever we define now here will be basis independent. And maybe once we have discussed that, it will be much clearer what the answer to your question should be or is.
Okay, thank you.
Okay, thanks a lot for the question. I think this is an important point, and as I said, we will come back to it. Now, the last thing I wanted to say, and then we are actually done, is we have now introduced vector fields, and I could now do everything we did for covector fields, of course. I mean, here it's probably obvious from the figure. Here I said to every point in the manifold, I associate TPM, and now we go from here to TPM, but I could also have done it with TP star M. So the summary of that, if you go back and do everything with TP star M, then we can say analogously, we can define something like the set of all covector fields. This is just by replacing all TPMs that occurred before by TP star M in the whole consideration we did so far. There's nothing else that changes because T star M, of course, also has dimension D and so on. Now, the only thing that should maybe be pointed out is that we can again then apply. So then we can apply, and by apply, you see, I always mean to act in the natural way with the object on another object. we can apply a covector field. So these are then covector fields. Maybe I should write this. This is covector field. We can apply a covector phi. So this is an element of this covector field to a vector field. So that's something new. So what do I mean by that? It's again just going back to the pointwise thing. So I take the covector field, and now I said it somehow acts on the set gamma m. So it takes a vector field and maps the whole thing to a function. Now, okay, you could probably guess what this should do. So first of all, it takes an element v, that's a vector field, and it should somehow make out of the v a function which I call phi of v. Now, what should this function be? Phi of v is just defined again pointwise. So if I apply this function at any point p, it should just be the same as if I applied the covector phi p to the vector at the point p. So I just do it pointwise, and pointwise you already know that the covector eats vectors. That was the whole definition of a covector. It's an object that swallows vectors and outputs a real number. So this is just a real number, and therefore I have already evaluated this function. So that's what this function here does. It takes a point and then just takes the covector at that point, applies it to the vector at that point, and that's the value of the function at that point. And now finally, we can define an RS tensor field. And then we have really all we need, because whenever we are with tensors, we are in the fully general regime. So what is an RS tensor field? This is, okay, maybe I don't even write this because it's written in the script, and I will have to write it anyway as a start for the Thursday lecture, because we will then prove a few properties about tensor fields. It's just the same idea that a tensor so far was just defined as a tensor on one tangent space. Now a tensor field is intuitively just a tensor at any point in the manifold. But again, we should think of it as a function that takes a point in the manifold and outputs the tensor in the course that is a tensor at this corresponding tensor at this corresponding tangent space. So I write here just this is defined analogously, but we will come back to it. So see next time. And that's probably also then an obvious time to stop the lecture for today. I think today was probably a kind of, in a way, I could say boring part, because we introduced objects that maybe are quite intuitive, so you don't see anything new really, but it has to be done because still you haven't seen vector fields on curved manifolds, but the whole essence of them, why they are different, and that, for example, curvature is defined with them, is something we can only introduce next time. So we had to go through that, but I hope that now we have the tools to at least do something that is new on the mathematical side, namely, for example, to introduce the curvature of a manifold, which is, of course, one of the key concepts in GR. Tomorrow we will start in this direction by defining a derivative on manifolds, which is called the Lie derivative. And I will, as usual, give you the physical meaning of that, and then we will proceed with mathematical definitions and properties. Okay, that was it for today. I hope to see you on Thursday.